Assalamu alaikum and welcome to Cambridge Chemistry channel with sarwatahmed. Be sure to like the video and subscribe it. Really helps the channel to grow. Today I will discuss buffer solution. Buffer solution is the type of solution which resists change in pH when small amount of acid and base is added. So buffer solution is the type of solution which resist change in pH when small amount of acid and base is added. A buffer solution contains number 1 a weak acid, for example ethanoic acid, number 2 sodium salt of weak acid, for example sodium ethanoate. The salt provides the anions of the acid CH3CO2 ethanoate. CH3CO2 negative is the anion of acid known as conjugate base of the acid. For example CH3CO2H ethanoic acid when dissolved in water to form CH3CO2 negative plus hydronium ion. This is weak acid and this is water act as a base. This is conjugate base of weak acid and this is conjugate acid of base. So the weak acid and its conjugate base are both responsible for controlling pH. Action of buffer. Consider a buffer containing ethanoic acid and its salt, sodium ethanoate. The following equilibrium established in the buffer solution. CH3CO2H plus water to form ethanoate and hydronium ion. Aqueous, this is aqueous. And we know that sodium ethanoate is strong electrolyte. Is strong electrolyte and ionizes completely in solution to give its conjugate base CH3CO2 negative ion. CH3CO2Na completely ionized to CH3CO2 negative plus sodium ion. So we can say that buffer contains mixture of CH3CO2H and CH3 CO2 Na. So the high concentration of high concentration of ethanoate ion in the solution suppresses the ionization of ethanoic acid. Hence, practically all of the ethanoic acid exists as undissociated molecule because it is a weak acid, or it is, look at this, it is partially hardly ionized in water. So this solution contains only ethanoic acid because out of 1000, uh, for example, one particle is dissociate into, so the this solution contain ethanoic acid because ethanoic acid is hardly ionized in aqueous solution. Hence, practically all of the ethanoic acid exist as undissociated molecule. Therefore, the buffer contains high concentration of weak acid, and its conjugate base, and high concentration of ethanoate ion. So, for this reason, small change in the concentration of the weak acid and its conjugate base have practically no effect on the pH of the solution. So, for this reason, due to the high concentration of weak acid and high concentration of ethanoate ion, small changes in the concentration of weak acid and its conjugate base have practically no effect on the pH of the solution. So, for example, when small amount of an acid is added to buffer, when hydrogen ions are added to the buffer, they combine with the ethanoate ions to produce, look at the, when hydrogen ion or hydronium ion added to ethanoic acid. So, ethanoic acid, when small amount of acid is added, ethanoate ion react with acid to form acid and water. So, it produces with hydrogen ion react with ethanoate ions to produce undissociated acid and water, hence pH pH of the buffer remains unchanged. So on the other hand, when small amount of base is added, next A when small amount of acid, and B when small amount of alkali is added to the buffer. CH3 CO2H plus. Now acid react with base to form ethanoate and water. So the OH ions of the alkali react with OH ion of the alkali react with the acid in the buffer to form ethanoate ion and water. Therefore the pH does not change. So the small decrease in the concentration of the acid, increase in the concentration of ethanoate ions have little effect on the pH because their concentrations in the buffer are very high. The small decrease in the concentration of the acid and increase in the concentration of ethanoate ion have little effect on the pH because their concentration in the buffer are very high. So when the buffer is most effective, a buffer is most effective when molar concentration of the acid and its salt are approximately equal, that is the ratio of their concentration is 1. In this situation both the acids and its salts have maximum relative concentration. When is a buffer most effective? A buffer is most effective when molar concentration of this acid and its salt are approximately equal. That is the ratio of their concentration, that is the ratio of their concentration is 1. In this solution, both the acid and its salts have maximum relative concentration. In this solution, both the acid and its salts have maximum relative concentration. There are two types of buffer. Acidic buffer mixture of weak acid and salts of weak acid, and this is the action when H positive ions are added. H positive plus CH3CO2 to form CH3CO2H, and when OH ions are added, OH negative plus CH3CO2H to form CH3CO2 plus water. So there are another types, that is the basic buffer. Basic buffer, it is a mixture of ammonia and ammonium salts. So when hydrogen ions are added, so it reacts with ammonia to form ammonium ion, and when OH ions are added, plus ammonium ion to form ammonia and water. So in this way, with addition of small amount of acid and small amount of base, resist the change in acid buffer as well as in basic buffer. So in this way the system maintains the pH. So calculations of the pH of buffer. Suppose a buffer contains a weak acid and Ha and its sodium salt Na. The acid ionizes as it follows. It contains weak acid CH3 COOH plus water to form CH3 CO2 and plus hydronium ion. Or we can use HA is the weak acid. For example, water H3O plus conjugate base. So the Kc is equal to concentration of hydronium ion and salt of weak acid negative ion divided by concentration of weak acid and water. Because water is constant, so Kc into water is equal to Ka, where Ka is equal to concentration of hydronium ion and concentration of weak acid ethanoate ion divided by concentration of weak acid. And H3O is equal to Ka concentration of acid concentration of base ethanoate ion conjugate base. pH is equal to concentration of hydrogen ion. Taking negative log of both sides, on the other hand we can use this relationship of the equation. We get pH is equal to pKa minus log concentration of acid or concentration of salt. For example, there is a question: calculate the pH calculate the value of Ka for chloric acid when it contains 0.050 mole Dm chloric 1 acid HClO and 0.050 mole sodium chlorate. pH is equal to 7.43 at 298 Kelvin. So we know that this is the HClO is an acid, weak acid, and NaClO is the salt. So we know that Ka is equal to H positive and salt of weak acid divided by concentration of weak acid. So in this question we know that pH of solution is 7.43. Now concentration of hydrogen ion is equal to 10 raised power to minus 7.43, which is equal to 3.72 into 10 raised power to minus 8. So Ka is equal to 3.72 into 10 raised power to minus 8. 0. Salt is 0.05 divided by acid is also 0.05. So Ka is equal to, cancel out, K is equal to 3.72 into 10 raised power to minus 8 mole Dm inverse cube. There is another question. Calculate the pH of buffer solution that is formed when 50 centimeter cube of 1.20 mole inverse cube ethanoic acid. So first calculate the mole of ethanoic acid is equal to concentration into volume is equal to 1.6 into 50 divided by 1000 is equal to 8 into 10 raised to minus 3 mole, and concentration of salt is equal to 8 into 10 raised mole over volume divided by, because 50 centimeter cube and 50 centimeter total is 100 centimeter cube, so the volume divided by 1000 is equal to 0.8 mole dm inverse cube. The next acid is concentration, mole of acid is acid is 1.2 into 1050 divided by 1000, so this is equal to 0.6 mole dm cube. Sorry, this is mole. This is mole of acid. Mole of acid. So the mole of acid is 0.06. So in this way, the mole concentration of acid is 0.6. So Ka is equal to acid and salt divided by hydrogen ion and salt divided by acid. So Ka is 1.74 into 10 raised to minus 5 is equal to H positive into 0.8 divided by 0.6. So H positive is equal to 1.74 into 10 raised to minus 5 divided by into 0.6 cross multiply divided by 0.8. So let's calculate. So H positive is equal to 1.305 into 10 raised to minus 5. Now pH is equal to minus log H positive is equal to 1.305 into 10 raised to minus 5. So the pH is to 4.88. So hope you will understand the calculation involving buffer solution.